Today we are solving frequency of the most frequent element. This problem statement is not straightforward. Let's try to break it down. The frequency of an element is the number of times it occurs in an array. You're given an integer array nums and an integer k. In one operation, we can choose any element in nums and increment it by 1. And we are allowed to do at most k such operations. So after performing at most k such operations, what is the maximum possible frequency of an element? Here are a couple of examples. In the first example, we can turn nums into 444 by performing 3 increments to 1 and 2 increments to 2, which is within the limits we are allowed to do. And now the frequency of 4 in the resulting array is 3. That's the maximum possible frequency we can achieve for a given nums and k equal to 5. In the second example, we can turn nums into this by incrementing 1 3 times, or this by incrementing 4 4 times, or this by incrementing 8 5 times. Each of these separately are less than or equal to 5, and in each of the resulting array, the maximum frequency is 2, whether it's 4 here, or 8 here, or 13 here. So we return 2. To come up with a brute force algorithm to solve this problem, let's look at a different example. Here is a different example. Let's work through this to come up with the brute force algorithm and optimize that to find the final solution. From the previous two examples, we can note one thing. After performing at most k increment operations, we get this resulting array. The maximum frequency in this resulting array is 3, and the integer that has the maximum frequency is 4. Notice this integer is always present in the input array. Same in the example 2. After performing at most k increment operations, this resulting array has maximum frequency of 2, and the integer that has that maximum frequency is 8, and this 8 is present in the input array. So we can note that the integer with the maximum frequency in the resulting array will always be present in the input array nums. So the integer with maximum frequency in the resulting array will always be one of these integers from input array. So how about for each integer in the input array, we check what's the maximum possible frequency after performing at most k increment operations. So for example, what is the maximum possible frequency of integer 5 after performing at most 4 increment operations? So we can only perform increment operations on the integers that are less than 5, because if we increment the number that's already greater than 5, we'll get even bigger after the increment operation. It can never be equal to 5. So we find the first closest integer to 5 and check how many plus 1 operations do we need to perform on that integer to make it equal to 5. In this case, we only need one increment operation to go from 4 to 5. Next, we find the second closest integer to 5 and repeat the same, which is 3. To make it equal to 5, we need 2 increment operations. Next, we find the third closest integer to 5, which is 1, and repeat the same. To make it equal to 5, we need 4 increments, which we cannot accommodate because we have already performed 3 increments before this, and we are only allowed to perform a maximum of 4 increments. This operation cannot be performed. So at most, we can convert 2 other integers into 5, making its maximum possible frequency to be 3. We repeat the same for all other integers, and we return the maximum of all the possible maximum frequencies. So the runtime complexity of this approach is big O of n because we are checking what's the maximum possible frequency for each and every integer in the input array. And for each integer, we find the first closest, second closest, third, fourth, so on and so forth, and check how many of them can we convert to that integer by performing at most k increment operations, which takes O of n square time. So the total runtime complexity is O of n cube. The square term is driving the runtime complexity to be higher. The square term is coming from finding the first closest, second closest, third closest, so on and so forth to the current integer we are checking. What if we sorted the input array and finding the first, second, third, so on and so forth closest to any integer is just checking the integers before it in the sorted array. So sorting the input array takes n log n time, plus once we have a sorted array, we have to go through each and every integer in the sorted array and check what's the maximum possible frequency of that integer after performing at most k increment operations, which takes O of n squared time. So the new runtime complexity is O of n squared. Simply by sorting the input array, we reduce the runtime complexity from O of n cube to O of n squared. We can reduce this n squared term even further to O of n by using a simple sliding window and a math trick, bringing down the runtime complexity to O of n log n, because we still have to sort the original input array. So let's see how can we do this final optimization using sliding window. Let me clean up some space here. First, we sort the input array, and for each integer in the input array, we check what's the maximum possible frequency of that integer in the resulting array after performing at most k increment operations. Notice when we repeat the same step for the next integer 4, we repeat comparisons with same previous integers again and again, which is what driving the runtime complexity to O of n squared. Is there a way to avoid these repeated comparisons? Let's see if we can use a sliding window to avoid these repeated comparisons. Let's say right now we're checking what would be the maximum possible frequency of integer 3 in the resulting array after performing at most k operations. We can convert 2 to 3 by using one increment operation, and we can convert 1 to 3 by using 2 increment operations, making it all 3s. And we used a total of 3 increments. For the next integer 4, instead of repeating comparisons with all these 3 previous integers, can we reuse this information to check if we can convert this window into window of 4s? So how many operations do we need to make this a window of 4? Sum of elements in this window is 6. To make them all 4s, we need at least these many operations, which is in this case 6, and that is clearly more than the allowed number of operations. So there is no way we can convert this window into a window of 4s, which means we have to reduce the window size. So we get rid of elements from the left side of the window because they are the farthest from the current integer 4. So let's reduce the window length to 2. To make this window of 2 4s, we need 2 operations, which is less than k equal to 4. So we can definitely make this window. The last 4 is the current element we are checking. So this is the maximum frequency of the 4s we can make. And we repeat the same for rest of the integers in the sorted array. So we are expanding the sliding window of n times and we are reducing the sliding window O of n times. Hence, we brought the runtime down from O of n square to O of n to find the maximum possible frequency for each integer in the sorted array, and it takes O of n log n to sort the input array, which makes the final runtime complexity to be O of n log n. So this is our final solution. Let's write the code for this. First, we sort the input array. Now start sort. Next, for each integer in the sorted array, we check what's the maximum possible frequency after performing at most k operations. As discussed before, we also try to maintain a sliding window that ends at the current integer. So for end in range length of nums. Next, we check if we can make the entire sliding window same as the integer pointed to by end. Nums of end. This is the current integer. And we want to check if we can make the entire sliding window current integer. So sliding window start is pointed by this, and length of the sliding window is n minus start plus 1, and we want to make this entire sliding window the current integer multiplied by sliding window. And we also need to calculate the current sum of the sliding window. So current sum is by adding this current element. So we initialize current sum to 0. So the number of operations needed to make the entire sliding window as current integer is this value minus the current sum. So while the number of operations needed is greater than k, we need to shrink the sliding window because we are allowed only to make at most k such operations. So we reduce the size of the sliding window by moving the start pointer 1. Before moving the start pointer, we need to subtract it from current sum. So current sum is equal to nums of start. And we can keep moving the start pointer as long as start is less than n. And the number of operations needed is more than k. So when the number of operations is less than or equal to k, that means the whole sliding window of length n minus start plus 1 has the same integer, which is current int. So that's the maximum possible frequency of the current int. So we can save this to the result. Let's call the result as max frequency and initialize it to 0 and update that over here, or the length of the sliding window. So that's it. We now return the maximum frequency. That's our code. Let's try to run the code. We pass all the test cases and let's submit it. That's our final solution. If you found this video to be helpful, please support by liking the video and subscribing to the channel, and I will see you in the next video.